What I want to show you today is known as ordinary least squares regression. And fortunately, this is intuitive to you for two reasons. Imagine you had the opportunity to win some money by playing a guessing game. Now, generally speaking, with guessing games, they're fairly random, right? Pick a number between 1 and 10, William.
5.
Why 5? It's right there in the middle. Pick a number between 1 and 1 million.
500,000.
See, you're no fun. Can't you just say 4? It's not in the middle. Our inclination, right, if we're playing a game, is you want to be close, right? So I'm closest if I'm in the middle. Mary Kate's like, no. What are you doing? You got a favorite number? You play birthdays? Like, no? Okay. Generally speaking, if we're saying pick a random number, lots of times you default to the mean. But if we're also playing a guessing game, it would be nice to have some information. Like, what is this number I'm guessing? Is the number between 1 and 1 million the weight of something? Is it the age of something? Is it a bank balance or a cost? Right? That's the whole thing behind game shows. Like, The Price is Right, they show you a thing and they're like, what do you think it costs? And there's some idiot that thinks a washer and dryer costs $4,000. And you're like, nope. I lived with a guy in college once. He had no idea what stuff cost. It's like, hey, Eric, I got to go to the store and get some butter. Oh, here's a 20. No. He's just like, here's my throw. And I'm like, how much do you think butter costs? He's like, I don't know, 12 bucks. So if we were to play a guessing game that involved money, but I don't have my wallet, so I can't actually flash any cash, and I said, guess how old my wife is. Well, she's not here, so she's not going to be offended, which is why I talk about my family all the time, because they're not here. Now, you could just guess a random number. You could use a measure of central tendency, which is kind of what you were doing, right? You were picking the middle between 1 and 10. You're like 5. According to the CIA World Fact Book, the average age of people is 38.5 years old. So if I were to say, William, guess my wife's age, you would say? 42. Just 38.5. All right, 42. If you could have one piece of information about me in order to guess my wife's age, what would it be? That's actually very tricky. 14 months. You want to know the difference in our ages? It's 14.5 months. I don't know. Am I? What year is this? Okay. Okay, but at least it would narrow it down. So you'd have you'd use my age, I guess, to guess her age. Actual data. All right. Does this help? Not you? Wow. Raise your hand if this helps you. Why does this help you?
Because if we look at your age and we go up to see like the number of dots and actually match up, we can use that to figure out the average and figure out what you're saying.
Okay, so you're taking an approach where you're saying, if I know where you're at, I can then get even closer at the average of your column of dots. Okay, so if, let me do the math. How old am I? My next birth, okay. So this is my column of dots. I believe I'm 39. Because really, once you're past 21, it doesn't matter how old you are. So I'm 39. 2017, yeah, 39. So you want to take 35 and 35, 36, 38, 39, 40, 41. Just average them all together. One small problem. What if there are multiple people that have 39-year-old spouses? What are you going to have? One dot. See, the way that this is overlaid, you don't know how many people are at these dots. But nice try. John? Well, that's what I'm going to teach you, yes. Well, what is that?
It's not like when you scatter plot, it's all condensed kind of like that. It's the constant average.
Nope.
Or it's like a trend of it.
All right. John knows what I'm going to teach you guys today. This, as a way of looking at data, is known as a scatter plot. And John wants a line of best fit. He wants the line that goes through this cloud of dots the best. Nope, the best. Okay, it's not about the number of dots you hit. It's about the line, the single line that represents the cloud the best. That's what we're going to learn how to do today. Now, I think this is an easy subject to teach because on the one hand, it's kind of like intuition. Like you already sort of know that if you want to know somebody's age, you'd want to know like my age. Right? You have in your minds intuition because generally speaking, when we think of the age of couples, we tend to think that people's ages and their spouse's age should be close. And if it's not close, what do we think about that? Ooh, right? We're like, something's going on here. You're 70, she's 40. You're old enough to be her. Dad, creepy, gross, ooh. Right? So we have in our mind these expectations that are already set up. Right? We see in this chart vast areas of emptiness. So do we see any 35-year-old husbands that have wives older than 40? No. So there appears to be some general rules here, like no wives 5 years older than you. There's a couple of outliers. Like, wife is 63, husband is 53. How much money does she have? How's her health? It just seems out of our expectation. And that's where I'm going with this, is that we very frequently have expectations when we think about relationships between two variables. The second reason that this is easy to teach to you guys is actually because of like middle school geometry. Because there was a time that you were in your math classes and you got to use that great and wonderful stuff known as graph paper. Or not, Gregory. All right? And it was like, nope, you can only do this using graph paper. And you learned things like your number line, the concept of negative numbers. And you also learned how to plot lines. And so you would be given like a set of coordinates. And the 3 is your x and the 6 is your y. And you'd go over and you put a dot at 3, 6. Remember that? Okay. You still have that in the back of your head. Ordinary least squares is the method that will give us that line of best fit. It's old, pre-computing. Legendre used this method in 1805 to describe the orbits of comets. And then once that paper was published, Gauss actually said, "Oh, you're using my thing for that?" And he says that he actually developed this method in 1794 in a working paper that, this is so easy, I don't even need to publish this. And so you have two people that are claiming to have invented a method. Legendre wins because he had the better name for it. It's the method of least squares. And in your mind, you're saying, oh, squares. I know why we put squares in, because we're going to be looking at the difference of something and we don't want it to cancel out. And that's exactly what we're going to do. To get back to what the book talks about, the book introduces this method of least squares as a form of correlation. And I don't like this. I don't like the correlation sort of framework, because correlation is not causation. Correlation is a way to describe how things maybe move together. And so this is the example I use. The higher the amount of correlation, the more movement you do jointly. So if I move my right hand when I'm holding my left hand, that's like perfect correlation. As the right hand moves, the left hand's going to move. But if I have no correlation, I can move the right hand with the left hand staying still, because they're not linked together. Correlation is a way to describe the amount of connectedness between two variables. If they are connected, we should see a pattern when we look at them in the scatter plot type graph. So we should see in this first one of a linear relationship, we can see that as variable x increases, variable y also increases. The cloud moves in the same direction. There's also what's known as nonlinear relationships. We end up with a parabola instead of a line, or an S, or any sort of weird, strange shape, but as the shape moves, so does the flow of the dots. We also, using correlation, can talk about how the relationships affect each other. So as x increases in a positive relationship, y also increases. If it's a negative relationship, as x increases, y decreases. So you can have both positive and negative correlation. These scatter plots show different levels of correlation. And you can see by the shapes of the clouds how strong the relationships are. So if there is no cloud and your dots are actually aligned, that's evidence of perfect correlation. They are moving together. There's no error, there's no weakness to that correlation. A 1 unit change in x results in a 1 unit change in y. Perfect correlation. As you go from a strong correlation to a weak correlation, the shape of the cloud changes. So this is still a pretty strong relationship between x and y, but it's a little noisy away from the middle. But if you draw a shape around it, it's very much an oval. Our next example C of a moderate relationship, the correlation is still there, but it's not as strong. So you get further away from the middle. And you still have an egg shape. We went from line to oval to egg, and now we're just at like circle blob. And there's no relationship here. you should be able to intuitively see where the line would go. So when we have this one, does that look about right? That looks about right. But if I were to do this, does that look right? No. That looks really completely wrong. I could do that, and you're like, maybe. But how is that any better than that or that or that? Right? Because you have this big giant blob, you can't really see the shape of it. We can numerically represent this relationship. It's known as correlation. The Pearson correlation coefficient is labeled R. And what the correlation coefficient does is it allows us to determine in the amount to which variables change overall, and then how much of that change is due to a second variable, which is covariance. So variance is how much the scores for each variable change. We know this. This is chapter 4, right? Variance is a measure of variability. We've already done that. S or sigma. But whenever we did that in chapter 4, we were always measuring the variable by itself. So how much does age vary within a group? And the only thing we're looking at is the age in the group. Covariance is how things vary together. And this is where you add in a second variable. So if we were to go around the room and measure every person's height and their weight, we would have variance. We would have variance in height, and then we would have variance in weight. And we can calculate that, right? From our sample, we can calculate the average weight in this room and the variance around that sample, the standard deviation. We can do that. You have that skill. Again, chapters 3 and 4. But what we're adding into it is the idea of covariance. Is there an effect on our weight due to our height? What do we think? Do we think as you get taller, you get heavier? You don't think so? What does it depend on? Well, let's think about this in the grand scheme. John is, from the table to here, is this tall, and he's about 40 pounds. Abby is about this tall, and she's about 60 pounds. So it seems like as we get taller as kids, we actually do gain weight, right? Because we have more mass, and it's just going up. But then you reach a certain point, and you don't have height go up anymore. You then expand outward. Right? So I would think that, at least in the growing part, that as we get taller, we probably get heavier. It is more mass. Right? Just say yes. Okay. So people who are taller should weigh more than people who are shorter. Okay. That's known as covariance. The effect at which our height has on our weight. Like I said, this can be calculated. And we can classify it, and essentially, again, inclination, the stronger the relationship, the higher the correlation. Now, the highest you can get is a 1-to-1 correlation, right? Which means perfect movement. That as we increase x, y also changes by some number of units, but a set number of units. That's when they're all on the same line. Every dot overlaps. Now the pitch of that line can change, right? Paychecks are like this. As you increase your hours worked by 1, you get a blank increase in your pay. And usually that's your wage. So if we're talking about minimum wage, every 1 hour you work results in a $7.25 increase in your wage. That's perfect correlation. Your wages are determined by the number of hours you work. That's perfect correlation. Let's just say, yeah, that's strong. So if you want to think about this as like a percentage, that's fine. How much of one variable is caused by the movement of another variable? I'm cool with that. You know the math sucks when we're not really going to use numbers and letters anymore. I'm just going to write out fragments. All right. R is equal to this thing divided by the square root of this thing times this thing. And we have whole words in there. That's not right. Again, I'm not teaching you math today. None of this I'm expecting you to do by hand. Today's all about the concept. R, which is our measure of correlation, is the extent to which X and Y vary together. So that's that covariance, how much movement you have together, divided by a measure of how much do they vary on their own. That's all this correlation coefficient is. It's just a measure of how much of the overall variance is due to them moving together. I think from 0 to 20, the correlation between height and weight is pretty strong. But then once you hit 20, it's like, nope, you're not growing any taller. You're just going to grow wider. And then the variation becomes not so much based upon the height, but it becomes based off of something else. Diet, exercise, genetics, whether or not you lose a limb. Right. So there is some variation on their own, right? And again, think about this. You stop growing taller, but your weight changes. And it fluctuates. That's the weight changing on its own. That has nothing to do with height. Don't copy any of this down. I do want to walk you through a little bit of the math. You could do this by hand. It's not that hard. All we're doing is taking a measure of the variation. So we know how to measure variation. We look at the difference between the observation from the mean, and then we square it because of this negative sign, and then we add them all together. That's the total amount of variation in our X variable. We do the same thing for our Y variable. The other one is the sum of the products of X and Y. And this is where we're taking the difference of both combined at the same time. So if I were to put this in the big nasty equation, you could do this, right? If I just swap out this SP of X and Y and the square root of the SX and the SSY. You can do that. That's not that difficult. And you would get something called an R, and you can go ahead and tell us whether or not that R is big or not. That's nice. That's your soft introduction to correlation. We're just another way of measuring the variance and covariance of multiple variables. But really what we want, like John said, is we want this idea of, I want to know the relationship between the two. With variation, with variance, all we get is the strength of the relationship. But we don't actually get the magnitude of the relationship. So if I were to tell you that your hours worked and your pay have very high correlation, you would go, okay, but what's the next question? Right? I'm offering you a job, Gregory, and all I'm going to tell you is that the more you work, the more money you'll get. Okay. The next question is, well, how much money? Okay. How much of a relationship? And that's where ordinary least squares come in, or linear regression. So when you were doing your 6th grade geometry and learning about lines on a chart, you were given this equation. Y equals mx plus b. Do you remember what m was? The change over the change, right? The change was usually the change of x over the change of y. So you were given, you had to compute that. And if you're doing a triangle, it's really easy because you just do the rise and the run. Anybody remember what b was? All right. The y-intercept is what? Where what equals 0? So where do you hit the y-axis at x being 0? That's the y-intercept. And then your slope was, oh, the slope is you go over this many and up that many. Yeah, flashbacks. You ended up with all these little triangles. But if you wrote the triangles on the graph paper, they would see what you were doing. And so you had to erase the triangles and do it really lightly. Really, that's what all you were doing. That's the slope of the line. Which you're thinking, I'm never going to use this in my life. Try building a set of stairs and not understand rise and run. Okay. So again, this is easy to teach you because you've already, again, you know what this concept is. We're going to change this a little bit, though. We're going to change the letters. It's the same format. But with ordinary least squares, what we're doing instead is we're trying to predict, we're trying to calculate our y variable. The book uses y prime. I like y hat. Different style of notation. Put a little caret over the y. Wearing a hat, that's a predicted y. So back to our original example, y hat is my wife's age. If that's what we're trying to predict, right? We're trying to guess, we're trying to know a number. Alpha, A, is our y-intercept. We're going to reclassify the m, because m looks a lot like what? Mu. Can't do that. We're actually going to make the m now the b. So mx plus b is now a plus bx. Sorry, not my decision. X, thank God, is the value of our variable. So back to our original example, x is what? If y is my predicted wife's age, x is what? My age. It's data we have, right? As long as I sit down and do the math, I can figure out how old I am. E, you know, E is actually an epsilon. E is there, but we assume it's 0. So lots of places just leave it off. E is that little bit of error that exists in the world, the reason we have outliers. There are also known as residuals. It's the unexplained part. E is your in Alabama, right? Things are just different in Alabama. Right? E is for the gold diggers. They're just out there, right? E is that extra little unexplained variance. E is those free spirits that say age is just a number. And what? I'm gonna steal the hell out of that. Age is just a number and jail is just a room. It's a good one. All right. E is the unexplained. E could be a missing variable, like in Alabama, or the income of the person being married. Right? E could be just the fact that I skipped a grade and was a year younger when I went to college and met my wife. Just random variance. Okay? Random difference. E's there. And in the next stats class, when you use the hell out of this linear regression stuff, you start paying attention to E. Because E can actually give you some information about what you're doing. The reason that a lot of stats books like to use correlation before they teach you regression is because we can take regression and we can do it in a variance framework. So the slope is just easy. You have R, which is the correlation between X and Y, times the standard deviation of Y divided by the standard deviation of X. Like, this is just a simple math shortcut to calculate the slope. Again, I don't know why you're copying this down, because I'm not going to ask you to actually do this. There are other ways of doing this as well. This is how I learned how to do it. I didn't learn ordinary least squares in a correlation framework. I learned ordinary least squares by trying to solve a problem of drawing our line. What you want to do is you want to draw the line in such a way that you minimize the difference between what you observe and what you predict. So let's take a moment here. I've removed the cloud because I want to, you should be able to sort of see this, but if I'll put the cloud up. Right, so there's the cloud. Right. What we're really doing is we're taking our predicted line and we're drawing the line in the spot that minimizes those errors. So it gives us our best chance at predicting. So we have the cloud all around. And if we were to just guess our dependent variable, which again, back to the original, was my wife's age, based upon the average age of all the people in the world, no matter how old I was, you would just keep saying 38 and a half. Right? I'm 60, she's 38 and a half. I'm 4, she's 38 and a half. I'm 20, she's 38 and a half. No matter what my age is, your guess is the average. Because I made a horrible guessing game and I didn't give you my age. Right? Guess the age of my friend Joe. You have no idea who Joe is or what his relationship is to me, but he's my friend Joe. How old is he? Gregory? Guess. 38 and a half.
38 and a half.
That's what you're supposed to guess. Joe's 5. He had a kick-ass birthday party this weekend. All right. That's my friend Joe. Joe's 5. But if you have an additional piece of information, all right, what benefit does that give us? Well, this is where they used correlation to help find the slope of this line. The goal with the line is that we can take the difference between all of the error that exists. So all of the error is the gap between the individual and right. So this right here represents all of the error. Our dot is actually up here, but we guessed down here. That difference represents all of the error. But how much of this gap can we take away by using that piece of information? So here we have our y hat. Right? We've predicted y. We've used our equation. We've predicted y. This is the amount of the difference. Let's see if I can. All right. This gap here is explained. It's explained by our variable that we introduced. That still leaves this gap here between what we predicted and what we observed. That's the unexplained variance. That's our error. So when we have something called the sum of least squares, we're trying to get this number of all of the errors that you observe in a data set to be as small as possible. That's the least part. Now we call them the squares. Why? Because we don't want them canceling each other out. So in order to take away the potential for that, you take a negative number, you square it, you can still observe the difference. Again, chapter 4. So that's why it's ordinary least squares. We've set up a way to try to explain as much of the variance in the cloud as possible. That's ordinary least squares. Here's the problem, and this is why this is a good place to stop. The problem is you use this when you have two variables that are continuous. So my age is a continuous variable. My wife's age is a continuous variable. That's when you use this. The math behind this is really hard because you can't make mistakes. When I had to learn this in grad school, I had to do a problem by hand. It had 13 observations. and I wasn't allowed to use Excel to just carry over all my calculations. I had to do this by hand. It takes a long time. There are ways to do this in, of all things, Excel. But what I'm going to do for the next half of this week's lecture, I'm going to post a video to show you some software that, again, if you continue on or you want to just get really good at doing what you already know how to do, that you can pick up and start to do this so you don't have to do everything by hand. So that's like, again, that's the next step. And if we had, you know, another 6 weeks, the rest of the class would be done using the computer. It's okay. There are other things that are better at it. So I'm going to show you that in the second half of the video. But for right now, you have an idea and a framework with how you would do this. You can actually do this in that SDA website. You can do it. It will do linear regression in the SDA website. You just got to play with it.